video introduces a very important type of constraint known as referential integrity. As a reminder, integrity constraints in a database restrict the allowable data beyond what's already restricted by the structure and types of the database. Now, the term referential integrity refers to integrity of references that appear in the database. In a relational database, a reference from one tuple to another occurs through specifying values, and referential integrity says that those values are valid. It's sort of equivalent to having no dangling pointers if we used pointers in the database. We'll see a number of examples. So let's look at our simple example database with the students, colleges, and students applying to colleges that we've been using for all of our demos. Let's suppose, for example, that we had a student 123 who had applied to Stanford for some major, let's say CS, with a decision of yes. When we have this tuple, the value in the SID field here of 123 presumably refers to a value here of an actual student. So maybe 123 is student Mary with some GPA in some high school. And furthermore, the Stanford value in the CNAME or college name attribute is presumably referring to the college name in the college table. So we would expect to have a Stanford value here. Referential integrity talks about these values here referencing the corresponding values in the other tables. Specifically, if we have referential integrity from an attribute A, say of a relation R, to an attribute B of another relation S, what that's saying is that every value that appears in the A column of relation R must have some corresponding value in the B column of relation S. So if we take a look at our example, we would say then that we would have referential integrity from the SID column of apply to the SID column of student. We would expect every value that appears in this column to also have a value in the other column. And similarly, we'll have referential integrity from the college name attribute in apply to the college name attribute in college. Again, we want every value that appears in this column to also appear in this column. Now, we might have a violation, for example, if we had a, say, 555 applying to Stanford for some major and some decision. If we have no 555 over in the student table, then this here would be considered a referential integrity violation. Similarly, we might have 123, which is valid because we have a 123 student here, but if 123 is applying to Yale and we don't have Yale over here, then again we have a referential integrity violation. Now let me mention that referential integrity is directional. So we talk about this SID here referencing the SID in the student table. We could have referential integrity in the other direction, but that's saying something different. That would be saying that every student must apply somewhere. Every value for student ID must appear in the apply table. In this particular example, we probably would not have that be the case. We would probably be able to have students who hadn't yet applied anywhere or colleges where no one had applied yet. And the most sensible direction for this referential integrity in this case is from the apply to the student and the apply to the college. But again, we could have it in both directions if we so wished. Now, just a few more details of referential integrity constraints. The referencing attribute, in this case the referencing attribute is A, is often called the foreign key, and in fact referential integrity is often referred to as foreign key constraints, and even in the SQL syntax we'll see that the term foreign key is used. Second, when we have a referenced attribute, in this case now we're talking about attribute B, so we have R.A to S.B, the referenced attribute is usually required to be the primary key for the table, for its table, or at least specified as unique. And that's more about efficient implementation than anything else, but it is a requirement in the SQL standard and in most systems. Third, it is possible to have foreign keys that consist of multiple attributes, just like keys themselves can be multiple attributes. Let's say, for example, that in our college relation, the college name together with the state form a key, not the college name individually. If that were the case, then our apply table would presumably have one more column that specified the state, so we knew which college a student was applying to, and in that case we would have these two attributes together as the foreign key referencing the college name and state together in the college table. And we'll see an example of multi-attribute foreign key constraints in our demo. Now let's talk about the enforcement of referential integrity constraints. First, let's think about what operations can occur to the database to violate a constraint. It's not every possible modification. So again, let's suppose we have r.a referencing s.b. So, for example, here we have apply referencing student and we have apply referencing college. So certainly if we insert a tuple into the referencing relation, so if we inserted a tuple into the apply relation, that could potentially violate the referential integrity if the values, say in SID or CNAME, didn't have matching values in the reference relations. Sort of conversely, if we delete from a reference relation, say we delete a student, then that could cause a violation because, say, we have the 1, 2, 3 value here, and the apply tuple that was referring to 1, 2, 3 after this is gone would then have effectively a dangling pointer. And of course, if we updated the referencing value, either of these columns, that could cause a violation if the new value didn't exist in the reference table, or if we update the referenced values, that could also cause a violation. In the SQL standard and in all implementations, if we have an insertion into the referencing table or an update to the referencing table that causes a violation to the integrity constraint, the referential integrity constraint, then an error is generated and that modification is not allowed, just like the violation of other types of constraints. For the reference table, however, table S, or in our case, table student and table college, if there are modifications that violate the constraint, if the referential integrity was defined initially with some special options, then it's possible for the database system to automatically modify the referencing table so that the constraint is not violated. So let's talk about that in a little more detail. Let's start by talking about deletions from the referenced table. So let's say we have our student 1, 2, 3 here, maybe 1, 2, 3 is applied a couple of places, and then we have our student 1, 2, 3 here in the student table. So right now, referential integrity is good. Everything's okay. But let's suppose that we delete the tuple with 1, 2, 3. So there's actually 3 possible things that can happen depending on how we set up the referential integrity constraint in the first place. So the default behavior is what's called restrict. So restrict is actually a keyword, but that's the default. And it says that if we do a deletion to the reference table and a constraint becomes violated, then we generate an error, just like I said before, and the modification is disallowed. The 2 other options are a little bit more interesting. One of them is called set null. And what set null says is if we delete a tuple in a reference table, then we don't generate an error. Rather, we take the referencing tuples, in this case these 2 tuples with 1, 2, 3, and we take away their SIDs and we replace those SIDs with null. And this is considered acceptable from a referential integrity point of view to have nulls in the foreign key column. So that will occur automatically. The third possibility is what's called cascade. So let's set up a little more data. Let's say we have 2, 3, 4 who's applied to Stanford, and we have Stanford over here. And now let's say that we again delete this tuple, so that would leave us with a referential integrity constraint violation here with this Stanford value. So what cascade says for the on-delete case is that if we delete this tuple, then we'll simply delete any tuple that has a referencing value. So this tuple will be deleted as well. Now the reason it's called cascade is because sometimes you can actually set up a whole chain of referential integrity constraints. So we have apply referencing college here, but maybe we'd have some other table referencing apply and maybe even another table referencing that one. And if we, say, deleted a tuple from college that caused us to delete a tuple from apply, if there was a tuple up here referencing that, we might get a delete there and then a further delete and so on. Typically, cascading will only go one step, but we'll see an example in our demo where we'll set it up where a cascade will go some distance. Now, updates have a similar 3 options. Let's erase all this stuff here. Let's again set up some example data. So let's say we have our student 1, 2, 3 who was applied to Stanford, and we have 1, 2, 3 over here. If we tried to update, say, this 1, 2, 3 to be the value 4, 5, 6, the restrict command would say that's not allowed because that would leave us with this dangling pointer and it will generate an error. The set null command will, similar to the delete, if this is changed to 4, 5, 6, set any 1, 2, 3 values to null. So in this case, we change 1, 2, 3 to 4, 5, 6 in the student, and then we would change 1, 2, 3 over here to null. Probably the most interesting case is the cascade case for the update. Cascade says that if we update a referenced value, then we'll make the same update to the referencing value. So let's say we have Stanford over here. In fact, we have to if we have the value, the referential integrity constraint being correct. And now let's say that somebody comes along and says, I think Stanford is spelled wrong. It's actually Stanford. Well, that's actually a common misspelling for Stanford. The first one was correct. But if someone makes this change, if we have the cascade option for the referential integrity constraint between apply CNAME and college CNAME, then that update will be propagated to any referencing values. So in that case, automatically, this Stanford and any other Stanfords in the apply table will be updated automatically to Stanford. Now let's take a look at referential integrity in action. Let's create our three tables. We create the college table with the college name as primary key and the student table with the student ID as primary key. That allows us to have referential integrity constraints in the apply table that reference those two attributes. When we create the table apply, now we're going to specify the attributes, and the keyword references says that we're setting up a referential integrity constraint from attribute student ID to the student ID attribute of the student table. And similarly, we extend the declaration of the college name attribute to have a referential integrity constraint to the college name attribute of the college table. We'll go ahead and create those tables. Now let's try to populate our tables. If we make a mistake, we try to put our apply values in first, but there's no data in the student table or the college table. So when we try to insert, for example, student 123 applying to Stanford, we'll get a referential integrity violation because there's no student 123 and there's no college Stanford, and similarly for student 234 applying to Berkeley. So we see the errors, and what we need to do is first insert the tuples for the students and the colleges, and then insert the apply tuples afterwards. So let's insert the two students, 123 and 234, and the two colleges, Stanford and Berkeley. No problem doing that. And now we'll go ahead and again insert the apply tuples, and this time everything should work just fine, and it does. In addition to inserts into the referencing table, we also have to worry about updates. So as a reminder, let's take a look at the students that we have. We have students 123 and 234. And in the apply, we have students 123 and 234, each applying to one college. Now we're going to update our apply tuple that has student ID 123. Our first update tries to set the student ID to 345, but we'll get a referential integrity violation because there's no student with ID 345. Our second update will be more successful. It will update 123's application to have student ID 234. We'll go ahead and execute the updates, and we see that the second one did succeed. So far, we've looked at modifications to the referencing table, but we also have to worry about modifications to the referenced tables. In our case, that's the student table and the college table. For example, let's suppose we tried to delete from the college table where the college name is Stanford. If we try to delete that tuple, we'll get an error because we do have an apply tuple that has the value Stanford and is therefore referencing the tuple we're trying to delete. Similarly, we can try to delete some student tuples. Let's go back and look at our apply relation, and we now see that both of the student IDs in apply are 234. So it should be okay to delete the student tuple with 123, nothing is referencing it, but it should not be okay to delete the tuple with student ID 234. And indeed, when we run the commands, we see that the first one generated an error and the second one succeeded. How about updating a referenced table? Let's say that we decide we'd rather have Berkeley called Berserkly. So we try to update that college name, but when we run the command, we get an error because we do have an apply tuple that's referencing the value as Berkeley. And finally, although we've been talking about data level modifications, referential integrity constraints also place restrictions on dropping tables. For example, if we tried to drop the student table, we would again get a referential integrity constraint because that would leave data in the apply table referencing non-existent data in what would now be a non-existing table. You can see that the error says you cannot drop a table student because other objects are currently depending on it. So when we have referential integrity constraints, if we wanted to drop the tables, we'd have to first drop the apply table and then drop the tables that it's referencing. Now we're going to set up the apply table to experiment with some of the automatic mechanisms for handling referential integrity violations. Specifically, we still have the same referential integrity constraints from student ID to the student table and from college name to the college table. But for the student ID referential integrity constraint, we're going to specify that if a student is deleted, then we're going to set any referencing values to null. And we do that with the keywords onDelete, which tells us what to do when there's a delete to the referenced table. We use the set null option. For the college name reference, we're going to specify that if the college is updated in the college table, and that says onUpdate, we'll use the cascade option. As a reminder, what that says is if we change the college name, then we'll propagate that change to any college names that reference it in the apply table. Now, I could have specified two more options. I could have specified an onUpdate option for the student ID and an onDelete option for the college name. So there could be four altogether. Because I left those out, those will both use the default, which is the restrict option, which says if you perform a modification that generates a referential integrity violation, then an error will be generated and the modification will not be performed, just as we saw in the previous examples. So let's go ahead and let's create the table, and then let's experiment with some modifications. Let's start by adding a couple more students to our student table. So then if we take a look, our apply table is currently empty because we just created it. Our college table has Stanford and Berkeley, and our student table now has three tuples, student IDs 123, 234, and 235. We'll insert 5 tuples into the apply table, and all of them are going to be valid with respect to referential integrity. We're only going to insert students that are 123, 234, or 345, and they're only going to apply to Stanford or Berkeley. So we've inserted those values, and now we'll perform some modifications to see what happens. We're going to delete from the student table all students whose ID is greater than 200. Going back and looking at that table, we'll see that student 234 and 345 are going to be deleted. Now remember, we specified onDelete set null for the apply referential integrity constraint. Specifically, when we look at our apply table, the references to the students that are about to be deleted should be automatically set to null when we run the update, when we run the delete command. So we'll go ahead, we'll perform the deletion. We'll take a look at the apply table. When we refresh, we see that those values have indeed been set to null. And if we take a look at the student table, we'll see that we only have student 123 left. Now let's test our cascaded update. As a reminder, when we set up the college name referential integrity constraint, we said that if we update the college name in the college table, we should propagate those updates using cascade to any references in the apply table. So we're once again going to attempt to change the name of Berkeley to Berkeley. This time it should allow us to do it, and it should change any applications to Berkeley to now specify Berkeley. So we'll go ahead and run the command, and we'll look at the apply, and we will see once we refresh that indeed Berkeley has now been changed to Berkeley. This example is a doozy. It's going to show a whole bunch of features that we haven't seen in previous examples. We're going to use a simple table T with just 3 attributes, A, B, and C, and we're going to say that A and B together are a primary key for the table. In the example, we're going to demonstrate referential integrity within a single table, so intra-table referential integrity. We're going to demonstrate referential integrity involving multiple attribute foreign keys and primary keys. And we're going to demonstrate a real cascading where we're going to have a cascaded delete that's going to propagate across numerous tuples. So typically one thinks of referential integrity as having a referencing table and then the referenced value exists in a different table, but there's nothing wrong with having referential integrity within a single table. For example, in the one attribute case, I might have attribute B where every value in B must also appear in value A, and that would be a referential integrity constraint within the table. In this case, things are slightly more complicated because I'm using pairs of attributes for my referential integrity constraint. Specifically, I'm going to have attributes B and C together reference attributes A and B together. Syntactically, to declare a multi-attribute referential integrity constraint in a table definition, I have to put it at the end because I can't attach it to a single attribute, just like I do when I have, say, multi-attribute keys, which is also demonstrated here. The syntax is that at the end of the table definition, I say that I'm going to have a foreign key constraint, and attributes B and C together have a referential integrity constraint to attributes A and B of the same table. Then, in addition, I'm going to specify onDelete cascade. That means if I delete a tuple, then any other tuple that's referencing the A-B values of that tuple with its B-C values will automatically be deleted. Okay? So let's run the table creation, insert our data, and then let's take a look at the table and predict what's going to happen when we actually delete a tuple. So here's the contents of table T after the insertions. So we see that A and B together do form a key. All of the AB pairs are unique. And furthermore, every BC pair has a corresponding AB value in the same table. So every tuple except the first, the BC pair references the AB pair of the preceding tuple. So we have 1, 1 here referencing 1, 1 in tuple 1. Our 2, 1 here references the 2, 1 in tuple 2, and so on. So our referential integrity constraints are intact for this table. What we're going to do is we're going to delete the first tuple by running a command that says delete the tuple whose A value is 1. When we delete tuple 1, because we have the cascaded delete set up, we will need to delete any tuple whose referenced values are 1, 1. So that will be tuple 2. So after deleting tuple 1, the referential integrity constraint enforcement will delete tuple 2. When tuple 2 is deleted, the 2, 1 value will be gone. So tuple 3, which references tuple 2, will be deleted. Then tuple 4, which references 3, will be deleted, and so on until the entire table is empty. So here's our delete command to delete the first tuple. We run the command. We go back and we look at the table, and when we refresh, we see that the table is indeed empty. That concludes our demonstration of referential integrity constraints. Referential integrity is actually extremely common in deployments of relational databases. The natural way to design a relational schema often has values in columns of one table referring to values in columns of another, and by setting up referential integrity constraints, the system itself will monitor the database and make sure that it always remains consistent.